Section 7. Yep, now we're going to talk about magnetic fields, which, as we'll see before very long, is not actually a distinct topic from talking about electric fields, although historically, for much of the past couple thousand years, they were thought of as being two distinct, unrelated topics. But to begin at the beginning, there are, like it says at the top of the page, two kinds of magnetic poles. This is very similar to plus and minus for electric charges. With magnetic poles, they're given the names north and south because, of course, the earliest applications of magnetism were in navigation. A magnetic compass is a really useful thing to have if you're sailing around out of sight of land and it's cloudy, so you can't see any stars, and you really don't want to sail around in circles until you run out of food and water. So opposites attract, likes repel, just like with electric charges. Just like with electric charges, the field vector, which is represented by the letter B for a magnetic field, just as an electric field points in the direction of the force on a positive charge, a magnetic field points in the direction of the force on a north magnetic pole. Same idea carried over. But then here's where we hit a difference. You can have electric monopoles. In other words, you can have a positive charge, an isolated positive charge, like, well, there's a proton right there. What's the direction of the force on that? That's the direction of the field. North magnetic poles, on the other hand, well, either kind of magnetic pole, are never found in isolation. You don't have a north without a south that goes with it, or a south without a north that goes with it. You only have dipoles, or combinations of them, like a quadrupole or something like that. So maybe a good way of, let me make a little sketch. Maybe a more practical way of defining the direction of the field. Here's an enlarged view of the needle on a magnetic compass. Pretty much the same picture I've got on the side of the page over there. A compass is just a permanent magnet that's been allowed to move freely somehow. One typical way of doing it is they just have like a little dent in the compass needle right at its center of gravity, and you can balance it on a needle point that way so that it'll turn any way you want. Or a somewhat cruder way of accomplishing the same thing, if you've got a permanent magnet laying around the house, you can just tie it to a cork or a piece of styrofoam or something so that it'll float in a bowl of water. One way or another, if you allow it to move in any direction it wants to, well, let's say there's a magnetic field pointing in this direction. That's the north end and that's the south end. The direction of the force on a north pole is parallel to the field. And just like with negative charges in electric fields, the force on the south pole is the other way. So this will create a torque that's going to make this needle rotate until, once it reaches this position here, neither one of those two forces gets any leverage, and that's where it'll be stable. So rather than saying the direction of the force on a north magnetic pole, the direction of the magnetic field is usually stated as being the direction that a magnetic compass would point. Okay. And I think that gets us through the first half of the page. Did I miss anything? No, we're down to there. I drew this little picture of the field around a permanent magnet. a magnetic dipole and sketched some field lines. And what the field lines mean, once again, is that if you put a compass here, so each of those little circles is supposed to be a magnetic compass, is the idea. So if you put a compass here, it'll point that way. If you put a compass here, it'll point that way, and so on. The field lines are showing you the direction that a compass would point at any, anywhere in the picture. And just like with electric field lines, their density shows you the strength of the field. Where the field lines are close together, the field is stronger. Where they're farther apart, they're weaker. Magnetic force on an electric charge. Well, electricity and magnetism were both discovered over 2,000 years ago. And for the first 2,000 years or so, they were thought to be two kind of similar, but just the same unrelated things. Because, well, I've put away my toys at this point, but if I had, remember that pith ball demonstration I did the first day? I had the little electrically charged ball hanging on a string. I brought a charged rod near it, and I made the ball pushed away like that, or if they were opposite charges, they were attracted. Well, if I had that charged ball and I brought a permanent magnet near it, the ball would just kind of hang there and do nothing. So, see, for about 2,000 years, all that anybody had to experiment with was static charges. And a charge at rest is, in fact, completely unaffected by a magnetic field. But starting in the late 1700s, electric currents were available. Volta had invented the battery and so on. And it turns out that moving charges do feel force in a magnetic field. And in fact, that's what you're going to be working with in about an hour when you do the lab. You may have noticed a rather large vacuum tube sitting on the end of each of your tables. And for some reason, the coils have been removed, but well, there's this, yeah, those things. Yeah, they fit into the base, one on each side of the, going to demonstrate for us. Yeah, and then the little black thing kind of pushes down into the base to kind of firm it up. You don't have to get too aggressive with it, but the coils will produce a magnetic field. You can see the electron beam on that screen that's in there, and because the screen glows where electrons hit it. The kinetic energy of the electrons is absorbed by the phosphor and re-emitted as visible light. So you'll be able to see the path of the electron beam across that screen inside the tube. And you'll see that when you turn on the magnetic field, the beam bends to one side or the other, depending on the direction of the field. So the magnetic force on an electric charge. A stationary charge feels no force because it turns out to be a velocity-dependent force. The formula for the force includes a factor of v, the velocity. When something is sitting still, that's 0. A moving charge does feel a force. The magnitude of that force, I'll just present this as being an experimental result. It's equal to QVB times the sine of theta. Q is the charge, goes with this picture right here. Maybe I should tilt this a little to one side. If you have a singly ionized atom and you have a doubly ionized atom shooting through the same magnetic field and the same speed, everything's the same except the charge. The doubly ionized atom will feel the force twice as big as the singly ionized atom. So the force is proportional to Q. If one charged particle is going faster than the other, all else being equal, you get a bigger force on the faster one. Not surprisingly, a stronger field gives you a stronger force, so F is proportional to B. And there's a sine theta factor. The magnetic force is the greatest when the charge cuts across the field lines. The charge is moving along the field lines. There is no force, no matter how strong the field is, no matter how fast it's moving, there is no force if theta equals 0, okay? Maximum when you're cutting across the field, in between angles, of course, in between amounts of force. So this is a little more complicated than what we had. Well, everything about magnetism is more complicated than what we had for electric fields. The force on a charged particle in an electric field is just F equals Q times E. Well, in this, we have the Q factor and we have the B factor, but there's also the V and the sine theta to make things kind of more interesting. So, I mean, this equation here was just a rearranged version of the definition for an electric field. What the electric field meant in the first place was the force per unit charge, E equals F over Q. If you wanted a similar definition for the magnetic field, you could call it the force per unit charge per unit speed, assuming that the particle is cutting across the field lines at 90 degrees. For a unit, force is newtons, charge is coulombs, speed is meters per second. That combination of units is named after Nikola Tesla. The SI unit is a Tesla.
I can only see Tesla as the person. It's really hard for me to accept that it's called Tesla.
Well, of course, now we're going to have a whole generation of people who think of Tesla as a car also. So it's turned out to be a popular name.
Well, because of absolute badass he was.
Yeah, and as things sometimes work out, I believe he died penniless.
And what do you mean? Make coils that sing, so
Anyhow, there is another unit I've mentioned there, supposedly an obsolete unit, but one that's still rather widely used. A Gauss is 1/10,000th of a Tesla. I think maybe Frederick Gauss lived a somewhat more happy life than Nikola Tesla did, but I'm not actually intimately familiar with his biography. A Tesla is a very, very strong magnetic field. The magnetic field of the Earth that you're sitting in right now is, I mean, varies a little from here to one point to another, but it's something on the order of 2/3 or 3/4 of a Gauss is what the Earth's field is. If you want something that's up into a whole number of Teslas, you're probably talking about a superconducting magnet. It's a pretty heavy duty magnetic field. Something in the milliteslas would be more like what you'd encounter from, you know, refrigerator magnets and that sort of thing. So that's the magnitude of the force on a charged particle, QVB sine of theta. As for its direction, yeah, well, here's where things get really interesting. In an introductory course like this one, I kind of like to try and restrict myself for the most part to problems that lie in a plane as opposed to three-dimensional type problems. Thing is, once you get into magnetism, there is no such thing. Magnetism is inherently three-dimensional. There's no way around it. The force on this charged particle is perpendicular to both the velocity vector and the magnetic field vector, which means it's either sticking out of the page toward you like that, or pointing through the page toward the people in the next room. To choose between those, Anybody remember the right-hand rule from Physics 131 when we did torque and angular momentum? And yeah, cross products. VB sine theta, if you think about it, looks a lot like the magnitude of a cross product. Magnitude of a cross product is the magnitude of the one vector times the magnitude of the other vector times the sine of the angle made by those two vectors when you stick their tails together. And the direction of the cross product is perpendicular to both of the vectors being multiplied, which is what I just got done saying is the direction of the magnetic force. And so the version that has the box around it, because it includes all the details, is that the force is Q times V cross B. Now, I should probably explain about all the little X's and dots you see all over this page here. We need some way of drawing an arrow perpendicular to the sheet of paper that you're looking at. Rather than hand out some sort of pop-up lecture notes like those birthday cards that you got when you were 4 years old, what's usually done instead is that a dot stands for an arrow that points toward you, and an X, you're looking at the back end of the arrow. I kind of get the idea that whoever thought this up was thinking about an actual arrow like an archer would shoot off of a bow. And the dot on the front, that's supposed to be like you're looking at the pointy end of the arrow. And the back end, I don't spend a lot of time shooting arrows, but I'm pretty sure that they actually have 3. So I would have used the letter Y rather than the letter X for that. But it's just another one of those things where nobody asked me, you know. And so it's like the whole thing about current being a scalar. I mean, if I were emperor of the universe, that would be one of the first things I would change. Not the first. I think I'd get rid of tooth decay before I worried about things like that.
How
But
do you just remove tooth decay?
I mean, if I were in charge of the universe, I would probably not qualify momentum with the letter P.
yeah.
Here's what I would do. I would change rho or the letter P to something completely different because they look exactly the same.
Well, rho's a little curvier, but yeah, I see your
Still
point.
looks like a P.
Yeah, and it's not a P. I mean, that is a Greek P.
That's a pi.
Well, actually, I think the Greeks pronounce it P.
That's a pi.
But regardless of how they pronounce it, that's what they use for that P sound when they're writing
Well, I'm
stuff.
gonna change it because I'm the ruler of the universe. What are they gonna do? Complain?
Ming the Merciless. Huh? That's you. Anyhow, so a couple of examples to get this whole right-hand rule thing rolling. In this first one here, let's say the velocity vector is right down the x-axis. So there's maybe some sort of an ion in the sun. The sun has a fairly strong magnetic field, especially around sunspots. It can be as much as 1,000 Gauss, as a tenth of a Tesla. So there's some, and you know, all the atoms in the sun are ionized. So it's going right down the x-axis. The magnetic field there points this way, meaning that's the direction a compass would point, except, of course, if we're talking about the sun, a compass would be vaporized and wouldn't point in any direction. But anyhow, point is, the direction of V cross B, first of all, before you do anything with your right hand, it's perpendicular to both of the vectors being crossed. So you know, if the sheet of paper here is the XY plane, then it's got to be either plus Z or minus Z. The right-hand rule is just for choosing between those two alternatives. If it's one of those short answer questions at the end of an exam, and the correct answer is plus Z, and you put down minus Z, I'm going to give you half credit for that because there's other people who are going to put down X and Y and just have no idea what's going on. If you, half the battle is just realizing that it's perpendicular to the plane of the page. To choose between those two alternatives, you wrap your fingers around the z-axis, pointing from the first vector toward the second one. With a cross product, the order matters. So from V toward D, fingers in my right hand, wrap around the origin. From the first vector toward the second one, my thumb points in the direction of the force, which in this example is out of the page. Over here, once again, the charged particle is going down the x-axis, but this time the magnetic field points in a different direction. Once again, it's got to be either plus z or minus z. To choose between those, you wrap your fingers around, you make like you're grabbing the z-axis with your fingers pointing from the first vector toward the second one. Order matters. Cross product is not commutative. This time my thumb points through the page. So you get one of those little X's for the force vector rather than the dot. Here's where I decided to write down how to calculate a cross product. What I had said last fall is just the first half of this. You've got two vectors, whether they're, if you're calculating torque, it's R cross F. If you're calculating this, it's V cross B. Just to generalize things, let's just call them A and C because I'm already using B for something else. What I said last fall is that the cross product is the magnitude of the one vector, and this is all in the back of your formula sheet. There's a section on one of the later pages where you can look this up. Magnitude of the one vector, magnitude of the other vector, times the sine of the angle between them, times a unit vector normal. That's why it's the letter N. In most of the I shouldn't say that. In these two problems I was just talking about anyhow, that would be either plus Z or minus Z. But N for normal, it's normal to the directions perpendicular, in other words, of both A and C. That's how you would, remember there's two ways of describing vectors. You can give their magnitude and direction, or you can describe them with their components. That's how you would get the cross product from the magnitudes and the difference in their directions, the angle between them. How to get a cross product from the components, I didn't take things quite that far last fall, but now I will. You calculate that determinant. That's how you get it from the components. Your basis vectors I, J, and K go across the top row. The components of the first vector go across the middle row, and across the bottom row, the components of the other vectors, the second one. Again, the order matters. You can't mix them up. So I should probably go over how to evaluate a determinant. And you don't actually have to do this. I mean, there's a brute force alternative. If you have like AXI plus AYJ plus AZK crossed with, I call it C, I guess, CXI plus CYJ, I'm running out of space. I think I'm going to make it CZK. You can just say this term crossed with that term, 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 this term crossed with that one, this one times that one, and then this one times that. 9 different terms altogether, and that'll get you the right answer. All the determinant is a way of kind of organizing all that arithmetic into a kind of what's often a convenient alternative. So if you have A cross C, it's equal to so what you do, I mean, you might pick a different row in some other kind of problem where you aren't doing a cross product, but the only sensible choice in this case is to go along the top row, the I, the J, and the K. You multiply each of those things times the 2 by 2 determinant formed by leaving out the row and the column like this. So you multiply I by the 2 by 2 determinant formed by leaving out the row and the column containing I. You multiply J by the 2 by 2 that you get, leaving out the row and the column containing J. Also, notice that you alternate the signs as you go along. First term positive, second term negative, third term positive. If it was a bigger determinant, you know, a 10 by 10, it would just keep going that way, plus, minus, plus, minus, plus, minus. K times the 2 by 2 that you get, leaving out the row and the column with K in it. I believe the technique, if I remember right, is called reduction of order. There is actually another way of evaluating a 3 by 3 determinant, but it only works for 3 by 3s. This approach works for any size, 7 by 7, 12 by 12. So when I took linear algebra, it's like, so there's two ways of doing this. One works all the time, the other one works for just this one special case. Well, being as lazy as the next student, I said to myself, I'll just learn the one that works all the time. I don't need that other one. And but anyhow, if you already know something about this stuff, yes, I'm aware there's another way of doing it. And if you like that, go right ahead. Let's see, I should probably, not sure if I left myself enough space. But yeah, that just barely fits. It says what I already said while I was writing it down. that you leave out the row and the column containing the quantity in front. And then, again, alternate signs as you write each term. So that reduces a 3 by 3 down to an expression containing 2 by 2s. How do you evaluate a 2 by 2? Downhill diagonal, A times D, minus the uphill diagonal, C times B. So you do that, and now you have a number. First determinant, that number is going to be the X component. This one will be the Y component, and so on. Time to show you that with some actual numbers in it, I think. So you have a beam of electrons in a cathode ray tube. Could be that tube sitting on your desk right there that you'll be working with in about a half hour. And I don't know, maybe I and J stand for east and north or something like that. Whatever you're using for your coordinate directions, those are the components of the velocity vector for each electron in the beam. This is the Earth's magnetic field at this particular location. J and K are probably horizontal and vertical because I don't know if you realize this, the only place the Earth's magnetic field is horizontal is near the equator. In this room, the field points at an angle something like that, okay? It's got a northward component and it's got a downward component. In the southern hemisphere, it would be north and up. If you're right at the magnetic pole down in Antarctica, the field points right straight up. If you're at the magnetic pole in northern Canada, the field points right straight down. So find the force on an electron in the beam. So this force we're being asked for is equal to Q times E cross B. For Q, it says it's an electron. You look up the elementary charge on your reference handout, your formula sheet, and do not forget the minus sign or it will reverse the direction of your answer. 1.6 into the negative 19 coulombs. Well, let's take this a step at a time. And then that charge, that scalar number, gets multiplied by V cross B. So I'm going to fill the numbers into that 3 by 3 determinant I was talking about. When you're taking a math class, the numbers always seem to be something easy to work with, like 3 or 7 or some such thing. But if you start trying to apply this to something real, then you get stuck with numbers like 1.6 times 10 to the 7th. So that's the X component of the velocity. Y component of the velocity is 2.9 times 10 to the 7. As for the magnetic field, it has no x component, that's just 0. The y and the z components were given in microteslas. If you want the force to come out in newtons, you have to convert microteslas into teslas. So 30 times 10 to the negative 6, 3 times 10 to the negative 5th, same thing. And negative 5 times 10 to the negative 5th. This is one of those things where it gets worse before it gets better. For the x component, take this 3 by 3 and leave out the row and the column containing I. For the y component, leave out the row and the column containing j. And for the z component, leave out the row and the column containing k. So that reduces it down to an expression with 2 by 2s in it. And the way you evaluate 2 by 2s is the downhill diagonal minus the uphill diagonal. So for the x component, that times that is what I meant by the downhill diagonal. This times 0, this is going to take up enough space on the blackboard as it is, so I'm just going to write down that that times 0 is equal to 0. For the j component, So that times that along the downhill diagonal, and the other diagonal, 0 times 0 gives me 0. One more. A lot of number crunching. It's kind of the thing they invented computers for. Okay, here's where it starts getting better again. Those brackets that's multiplied by I, that works out to negative 1,450. $800 for the y component. This is the y component of v cross b. I still have to multiply by the charge. And I'm just about done. You distribute the negative 1.6 times 10 to the negative 19. And of course, half a point off if you don't label the unit. It's a force, so it's in newtons. And we'll just pause a minute while everybody gets all those numbers written down. Tiny newtons, yep. Now, what I'm going to do for the last 10 minutes of the class here is I'm going to skip over example number 2. We'll come back to that on Monday, but I want to talk about what's on the top of the next page because that ties in with the lab. We'll take things slightly out of order here. Based about is how that if a charged particle is moving perpendicular to a uniform magnetic field, its path is a circle. This differs from the other kinds of fields we've talked about so far. If you take a baseball and you throw it through a uniform gravitational field, near the beginning of Physics 131, I did projectiles. That baseball follows a parabolic path. An electric field is really the exact same situation. If you shoot an electron through a uniform electric field, once again, parabolic path. It's just like a baseball, only it's a lot smaller and going a lot faster. But in a magnetic field, it's a little different because when when a baseball goes through a gravitational field, the force on the baseball is always downward, no matter what the direction the baseball is moving. You shoot a charged particle through a magnetic field, the direction of the force is always perpendicular to the direction of motion, rather than being a permanent direction like you have with a projectile. So over here, we have a region with a uniform magnetic field, which incidentally is usually the biggest problem getting a good result out of today's lab experiment, is that the field is not quite as uniform as you might like. The ones that work better, the ones that are like $1,500 or $1,800 per setup instead of being just some, you know, it was years ago I bought these. I don't know what the replacement value would be anymore, but point is they've got bigger coils, okay, 2 or 3 times the diameter of those. And that works a little better, I guess. I've never actually had one because I didn't think it was worth the money, but that's the excuse if you get kind of iffy results on this one, is that the coils don't produce, although sometimes it works pretty closely. But anyhow, uniform magnetic field, and an electron which is produced somewhere over here beyond the edges of the picture. It gets shot into this field at this point right here. So when we first look at it, it's moving horizontally, and if you do all the right-hand rule stuff, well, I should probably demonstrate, because you're going to have to do this for yourself in the lab. So the red one is the magnetic field. Sometimes I like to build little models out of pencils like this. The red one is the magnetic field, and the yellow one is the velocity vector. The force has to be perpendicular to both of them, so that would be either up or down. You get your right hand, you wrap it around that axis, pointing from the first vector toward the second one. So like it shows here, V cross B points upward. But since it says it's an electron, well, it doesn't say it's an electron, it just says it's negative. Since Q is a negative number, that reverses the direction. Q times V cross B has the opposite direction compared to V cross B. The first thing you do in the lab is you're supposed to see for yourself that electrons are negative. I mean, why should you believe me, you know? You go around believing people, you can end up buying a pretty lousy used car that way. So you're going to shoot the electrons through a magnetic field and do everything I just did. And notice that the direction that the beam bends, which would be the direction of the force, is opposite of the direction that V cross B points, which would indicate to you that Q must be a negative number. Anyhow, because there's a downward force, the electron starts to move downward. So in the next picture of it, it's not only moving horizontally, it's got a downward component to its velocity also. Well, the thing that's different from a baseball is the direction of the force kind of swings around. It has to stay perpendicular to the velocity vector. So now the force is that way, which pulls the electron more in that direction. So in the next picture, now the electron is moving this way. Well, with a force on it pulling that way, in the last picture, the electron is going in that direction. And if it doesn't run into anything first, it'll just keep going around. Notice that the force always points toward the same point somewhere in the middle. This is uniform circular motion, like physics 131, where you did that lab with the rubber stopper on the string that you swung around over your head. So anytime something is in uniform circular motion, the net force on it has to equal mv squared over r, as I showed you in detail last fall. So this magnetic force is providing the centripetal force. Again, anything in uniform circular motion, the net force on it is equal to mv squared over r. The magnitude of the magnetic force, absolute value signs because I'm talking about its magnitude, theta is 90 degrees because it says there the charges are moving perpendicular to the field. If theta is not 90 degrees, rather than a closed circle, you get a helix, okay? If you've got a magnetic field line going along there like that, charged particle will corkscrew around it. This is what happens, for example, when charged particles from the sun hit the Earth. They follow the magnetic field lines toward the magnetic poles, going around them like that. And near the magnetic poles, they come down into the upper atmosphere and make the upper atmosphere glow. And that's why you get auroras at high latitudes, and they're fairly rare here where we are, and even rarer if you live in Ecuador. But sine of 90 to get a closed circle rather than a corkscrew, theta has to be 90 degrees. And so that's equal to 1. One of these v's gets canceled by that v there. And if you rearrange things a little bit, so for example, any of you who might be thinking of being chemistry majors or something like that, this is how a mass spectrometer works. You have a sample of some unknown material, and you vaporize your sample. Unfortunately, a lot of identification techniques involve destroying the thing that you're trying to identify, but you have to vaporize at least a little bit of it. And you break out, separate it out into a whole bunch of ionized atoms. Because they're electrically charged, you can accelerate them with something kind of like an electron gun, except it would be an ion gun if you're shooting ions through it. You shoot them into a magnetic field. Well, you can separate the atoms of different elements based on their masses, okay? Some lightweight ion, like hydrogen or something like that, would follow a path with a small radius. Some heavier ion, like, oxygen would follow a bigger radius. Iron would follow a radius even bigger than that. And so there's some sort of a detector along here, and one element hits it here, and another element hits it there, and another element hits it there. And you can do that to determine the chemical identity of the thing you're trying to analyze. That would be one application of it. Or the application you're looking for today is that this is part of the story of how Thomson measured the charge to mass ratio. See, this was before Millikan's oil drop experiment. Millikan was what, 1909 or something like that. Now, today it's 1897 in here, if I remember the year correctly. So,
I'll look up my right to vote.
well, just, there's no election today anyhow. So if the charge of the electron was already known, what Thomson would have been doing is determining the mass of the electron. As it is, he was only able to determine the charge to mass ratio. But the fact that it was always the same demonstrated that electrons were particles. You see, people, once good vacuum equipment became available, once you could take a glass tube and suck all the air out of it to a nice hard vacuum, it was fairly quickly discovered that if you had some electrodes inside that tube and applied a high voltage, there were some sort of rays coming from the cathode, which they called cathode rays, surprisingly. And well, what were these things? Nobody knew for a little while, but Thomson was able to show that they were some sort of a stream of particles. Because if it was just a wave, like you have on the surface of a pond, for example, you wouldn't have this well-defined charge to mass ratio. And so that was the discovery of the electron at that point. Thomson was the first person to discover an elementary particle, I guess is the way we would put it today. So anyhow, I think I've gotten you through enough of these notes to understand what's going on in today's lab. I should stop recording. The answer sheets for the lab are right there.